interactions. So
for sure, yeah. This is cool. It's the first time I've ever been live streamed on YouTube. So
there you go.
We'll see how many viewers we get.
Yeah, our web developer for CGD, oh, sorry, I'm getting your feedback. Yeah, he was like, no, we need to start doing this. And he was totally right. I think, I mean, we don't get a lot on the live YouTube, but I mean, you know, it's still helpful to people.
I've actually gone and watched some talks on just the NCAR YouTube channel before, and it's just nice having them there as a resource. Like even like a talk that's like 2 years old, go back and rewatch it. Yeah.
Yeah, absolutely.
I'm going to mute myself, but thank you, Mitch.
Great. Yeah. Thanks, Tracy. Nice meeting you. So did you hear, Patricia, that they finally got rid of the vaccine requirement or they got rid of the test requirement to enter Canada?
They did?
They did, apparently.
I did not. Yeah, I haven't been following because, I mean, I went for the holidays, and since I'm not planning on going soon, I haven't really been following, but that's totally interesting. Is the vaccine requirement still there?
Yeah, so you don't, if you're vaccinated, you don't need a test to get in. Is the
okay.
Yeah.
Okay.
So I'm actually flying back next week for my grandma's 90th birthday. So
oh my God, that's awesome.
Excited for that. Yeah.
That's gonna be great.
Yeah.
Hopefully the weather's not too bad at this time of year in Winnipeg. I don't know.
It's super snowy. Whenever I FaceTime my parents, it's just like these mounds of snow in the backyard. So
oh my God. My parents have been like working really hard these past few weeks, collecting maple sap. Apparently it's like cool. It's been flowing really a lot this year. They've had like good temperature, like warm during the day and cold during the night. So they've been making maple syrup every week, which is really exciting.
Awesome. Yeah.
Yeah.
It's unfortunate when your family does something really stereotypically Canadian though, right?
Yeah, I feel like I talk about it with people here and people are just like, you Canadians and your maple syrup. So, anyways, but yeah, it's pretty fun.
Hey, Gustavo. Good to see you. Yeah, long time. It's been a while. Yeah. I feel like I've seen you on a few Zooms here and there, but not face to face in a long time. Yeah.
You should come over and visit us.
Would love to. Yeah. I'll look for a meeting at NCAR and try to make it out. Yeah. Hey, Marika.
Hey, Mitch, how are you?
Good to see you. Yeah, doing pretty well. Yeah.
Good to see you too. And I agree with Gustavo. You should come visit us.
Yeah, would love to. I'd love to. Yeah. Yeah. Do you normally, I guess before the pandemic, you normally would like bring speakers in for this seminar, I assume, or was it actually virtual before the pandemic?
It wasn't virtual, but I'd say more speakers were local or, you know, maybe come up from the university or CSU, but kind of local to the area. I don't think we had a budget to fly people in. So
yeah, it feels a little wasteful flying across the country for a 1 hour talk, kind of. Yeah.
Yeah. But when we had visitors, we would ask them to give talks too. So that's the way to do it. It's like, have you come visit us for a week or so, and then also give a seminar.
Yeah, exactly. Yeah. Yeah, would love to come out and hang out with you and Lorenzo and the rest of the Sea Ice crew. It'd be a lot of fun.
Yeah.
Awesome. Well, I think we're going to get started. So hello, everyone, and thanks for attending today's CGD seminar. For those of you who don't know me, my name is Patricia de Repentigny. I'm an ASP postdoc in the PPC section here in CGD. And today I'm filling in for Dan, who's out on vacation. Before we get started, I'll remind everyone of our code of conduct at these seminars, where we share the air, acknowledge teamwork, encourage innovation, show appreciation, consider new ideas, and offer constructive feedback. I'll also ask that everyone please keep themselves muted and hold questions, any questions until the end. although you should feel free to enter questions in the chat as they come up. Now it is my pleasure to introduce today's speaker, Mitch Bushuk. Mitch is a research scientist at GFDL since 2017. He received a bachelor's in mathematics and physics from the University of Toronto and a PhD in mathematics and atmosphere ocean science from New York University. Mitch's interests and expertise include sea ice variability and predictability, polar oceanography, sea ice and coupled climate modeling, data assimilation, and geophysical fluid dynamics. The title of his talk today is Sea Ice Prediction in a Changing Cryosphere. Can we, have we, will we? So Mitch, feel free to share your screen and take it away.
Great. Well, thanks so much, Patricia, for that intro. Yeah, I'll just go ahead and share my screen here. Okay, so I hope that looks okay. Excellent, great.
Yeah, looks great.
Yeah, so yeah, thanks a lot, everybody, for taking the time to tune into this talk today. It's nice to see a lot of familiar names and names in the participants list, and yeah, it should be a lot of fun. So yeah, just before I dive into the talk, I'd like to say a big thanks to all my co-authors whose names are listed here, who have contributed to different aspects of what I'll be speaking about today. Okay, so this talk is focused on sea ice, and as we know, sea ice is this really fascinating multi-scale geophysical material, and it exists at the interface between the atmosphere and the ocean, and as such, it's forced both dynamically as well as thermodynamically by both of those media. And then sea ice additionally has a whole host of really fascinating small-scale physics that characterize it, such as the formation of these sea ice leads, interactions with ocean turbulence, the formation of these surface melt ponds in the summer, the formation of sea ice flows, these pressure ridges, and another picture here of sea ice leads. So this whole kind of host of different spatial and temporal scales and different processes kind of all conspire together to ultimately give us what we see in the sea ice observational record. And so here's what we have for based on the passive microwave satellite sea ice observations, which go back to 1979. So we have an over 40-year record now. And on the left, you can see the well-known decline of September Arctic sea ice extent. And that's been contrasted by this relatively flat evolution of Antarctic sea ice extent, which, if anything, has shown a bit of a positive trend over the satellite era. Now, in today's talk, I'm going to be focused mostly on these interannual fluctuations that we see relative to this long-term linear trend, and trying to answer the question whether or not we can predict these interannual variations that we see in sea ice, and on what timescales we can skillfully predict those interannual fluctuations. Okay, and I'm going to frame this talk around these three questions: can we, have we, and will we? And this is inspired by a really nice paper by Libby Barnes and James Screen, who used sort of the same framework to investigate whether Arctic sea ice can influence the mid-latitude jet or not. So in the first part, I'm going to deal with this can we question, and I'm going to attempt to present the scientific basis for sea ice predictability, why we think sea ice predictions are possible. Then in the second part, I'm going to address the have we question, and I'm going to show some performance of sea ice predictions from two dynamical prediction systems that we've developed at GFDL. And then in the third part, I'm going to move on to the will we question, and I'm going to highlight some existing challenges that we have in sea ice predictions and also some potential for future improvement. Okay, so with the decline in Arctic sea ice, there's been a lot of interest in both the scientific and the stakeholder community in this question of making seasonal sea ice predictions. And there's been a really nice effort put together by a group known as the Sea Ice Outlook, which has sort of formalized this prediction effort. And the Sea Ice Outlook requests predictions of September sea ice extent every summer. And they ask for predictions initialized in the months of June, July, and August. And then ultimately those predictions can be compared against the observed value. So here I'm showing the 2021 observations. And you can see that this collection of predictions doesn't look overly good, I would argue. Most groups underpredicted the sea ice extent by a fairly notable margin that would be on par, if not larger, than the interannual variability of the sea ice itself. Actually, here I want to highlight there's the NCAR prediction was around 4.1, and this was based on the NCAR sea ice pool. So the pool guesses were not that great last year. Okay, so seeing that plot, you might be a bit pessimistic, and you might it'd be natural to ask, do we think there is predictability for sea ice? And so I'm going to lay out some of the reasons why we think that there should be predictability and focus really on the seasonal to interannual timescale here. So the first source I want to highlight is simply radiative forcing. So if you take a modern GCM, such as a CMIP6 model, and then you force it with historical estimates of radiative forcing agents, you find that the typical CMIP6 model is able to reproduce an Arctic sea ice trend that looks pretty similar to what we get in the observations. Of course, speaking at NCAR, I don't need to emphasize this, but internal variability is very important to think about in this problem. And if you run the same model under the same historical forcing, you can get quite large differences in sea ice trends. So internal variability is also something to keep in mind in terms of representing these trends. Now, on the seasonal to interannual timescale, a whole host of other physical mechanisms become more relevant. The first of which is the simple persistence of sea ice extent anomalies. So what's plotted here are lag correlations of sea ice extent in different initial months, and then correlated with future sea ice extent. And what you see is that there's this characteristic sort of 2 to 5 month decorrelation timescale of sea ice extent anomalies. And then there's also this interesting reemergence that occurs of correlation at certain lag times. And associated with this inherent persistence, you can imagine that there'd be some associated predictability for sea ice. Sea ice thickness is another really key source of predictability. And relative to sea ice extent, sea ice thickness tends to have longer spatial autocorrelation length scales, and also longer temporal autocorrelation time scales. So shown on the left here is an estimate of those spatial autocorrelation length scales, which are around 1,000 meters typically for thickness anomalies. So these are quite large scale anomalies. And then on the right, I'm showing lag correlations of sea ice volume computed using GCMs. And GCMs typically show sort of a multi-annual persistence of sea ice volume anomalies. And sea ice thickness couples very strongly with sea ice extent, especially at the end of the melt season, because the initial thickness of the ice in the spring, let's say, will dictate how much energy is required to melt that ice away. And therefore, knowing the thickness should give you some predictability for knowing what the late summer sea ice extent should be. Another key source of predictability, which is more relevant in the fall and winter months, is the heat content of the upper ocean. And the idea here is basically that the upper ocean stores some amount of heat, and the amount of heat in the surface ocean layer will modulate. Oh, sorry, my dog's barking at the mailman. The amount of heat in the upper ocean will modulate basically how easy or difficult it is to grow sea ice in the winter. So the basic relationship is that if you have an anomalously warm subpolar ocean, it's going to be harder to grow ice. You're going to have negative sea ice extent anomalies, and then vice versa. A cold ocean tends to correspond to positive sea ice anomalies. So you get this pretty robust covariance between the two. Surface melt ponds have also been highlighted as a key source of predictability. And so just as a reminder, these melt ponds are pools of meltwater, pools of melted snow that form on the sea ice surface in the spring. And authors have found that if you correlate the aerial coverage of spring melt ponds with September sea ice, you get a pretty high correlation. And the mechanism here is just simply the ice albedo feedback. So if we have more surface area covered by melt ponds, we tend to absorb more shortwave radiation earlier in the season. That tends to increase surface melt as well as bottom melt of the ice. And that tends to sort of lock you in to either a high anomaly or low anomaly sea ice extent state, which persists all the way through until the September sea ice extent minimum. Okay, atmospheric modes of variability are also another key source of predictability for sea ice. And what I want to highlight here is the impact of the North Atlantic oscillation. So shown on the left here is the loading pattern of the NAO. And the NAO tends to force these dipole type anomalies between the Labrador Sea and the Greenland and Barents Seas. And there's been this really interesting body of work coming out of the Met Office in recent years, which has shown that the winter NAO index could be skillfully predicted a few months or maybe even up to a year in advance. And so you can imagine that if you could predict the NAO with some skill, that should give you some associated prediction skill for sea ice anomalies via this loading pattern and this teleconnection between the SLP and the sea ice. Okay, and now the final source I want to highlight is the large-scale circulation of the ocean. And the idea here is that if you could predict some sort of metric of large-scale ocean circulation, like for example, the AMOC or the subpolar gyre transport, that should give you some predictability for the northward heat transport of the ocean into the Arctic. And that heat transport will therefore will eventually modulate the heat that actually gets delivered to the ice, and that should give you some predictability for the eventual sea ice extent. And there was a nice paper by Steve Yeager a few years back where he showed that in a decadal prediction system, you can skillfully predict decadal sea ice trends, both in the Arctic as well as the Atlantic portion of the Arctic. And he attributed this skill to initialization of the ocean component and then the associated predictability of the North Atlantic subpolar gyre. So these mechanisms are thought to be more relevant on sort of the decadal timescale and may require some sort of temporal averaging or low pass filtering to see the signals. Okay, so another really key piece of our evidence comes from these so-called perfect model predictability experiments. And these experiments seek to answer the question, what are the upper limits of Arctic sea ice predictability? And so the idea is you take a GCM and you initialize it with nearly identical initial conditions. Then you run that model forward in time. And as time runs forward, these individual ensemble members will spread out under the chaotic dynamics of the system. And at some time, the spread of this ensemble will be equal to the climatological variance of the free running model. And at that time, you would say that we had reached the limit of predictability, and there was no more predictability left in the system. Another sort of visualization of that is shown by this kind of cute triple pendulum system. And so this shows an ensemble of different pendula initialized from very similar initial conditions. And you can see that the motion is predictable for some amount of time. And then you get this fairly spectacular kind of transition to chaos and a loss of predictability at some time. So we can characterize these temporal limits of predictability for the Arctic. And these perfect model experiments have been run with a number of different GCMs. And these GCM experiments have estimated that Pan-Arctic sea ice extent should be potentially predictable somewhere between 12 and 36 months in advance. Now, these perfect model predictability estimates do come with an associated warning. And in a study that Ed Blanchard Rigglesworth and I did a few years ago, we found that you can explain the differences in perfect model predictability between different models via their differences in persistence. So you can explain the differences in winter predictability via their year-to-year sea ice extent persistence, so the correlation from year to year of March sea ice extent anomalies. And similarly, you can explain the differences in summer predictability via their year-to-year persistence of September sea ice extent anomalies. So what this implies is that in order to trust a given model's predictability estimates, a necessary condition should be that that model does a good job of simulating persistence that looks like nature's persistence. And unfortunately, if you look at the observed persistence, which is shown in this asterisk here, nearly every model in CMIP5 that we looked at was over persistent in terms of winter sea ice and was also over persistent in terms of summer sea ice. So what this implies is that the predictability estimates we get from GCMs are likely too confident, and they're likely overestimating the true limits of predictability. Okay, so that brings me to the end of this first part. And so hopefully I've convinced you that the answer to the can we question appears to be yes, but it's important to note that the true limits of predictability are still uncertain. Okay, so now I'm going to move into the second question of have we? And in this part, I'm going to show some results from two dynamical seasonal prediction systems that we've developed at GFDL in recent years. And so these systems are called FLOR and SPEAR medium. FLOR stands for Forecast-Oriented Low Ocean Resolution, and SPEAR is the seamless system for prediction and Earth system research. Both of these models are fully coupled global dynamical models, and you can see that they both have the same 1 degree resolution in the ocean and sea ice components, and also a relatively higher resolution of 0.5 degree in the atmosphere and land components. FLOR was our previous generation seasonal prediction system, which was sort of retired in 2020. And then the SPEAR system was developed based on all these new CMIP6 model components that were developed at GFDL for CMIP6. And we've built this new prediction system based on those components. Okay, so a really key aspect of these systems is how we initialize them for forecasts. So in both systems, we're assimilating a variety of different oceanic and atmospheric observations. In the ocean, we're assimilating satellite sea surface temperatures, temperature and salinity profiles coming from Argo floats, XBTs, and moored buoys. And we do this at a daily frequency. In the atmosphere, we assimilate three-dimensional reanalysis data, and we're using NCEP2 in the floor system, and just using temperatures in that system. And in SPEAR, we're using three-dimensional temperature, winds, and humidity from the CFSR reanalysis. And we're doing this at a fairly high frequency of a 6-hourly assimilation. And then in terms of sea ice data, there's no sea ice data explicitly assimilated in the floor system. And in SPEAR medium, we do use sea ice concentration observations to adjust the under ice SST values, and we do that with a daily frequency. And so you can think of this as sort of a very crude form of sea ice data assimilation. We actually have a more proper treatment of sea ice data assimilation, which Yangfei Zhang has been leading. And we have a version of SPEAR with sea ice DA, but I'm not going to speak about that at all today. And then in terms of data assimilation methods, we're using the ensemble Kalman filter in both systems. And then in the SPEAR system, we also have this additional step of doing a nudged atmosphere and SST run of the coupled model. And we use that run to initialize the sea ice, atmosphere, and land components. Okay, and then we've used, using these systems, we've ran these suites of retrospective seasonal predictions. And so these are seasonal forecasts initialized on the first of each month and then run for 1 year of time as an ensemble. And we use 12 and 15 members respectively. And we've done this for every year and every start month from January 1992 until December 2020. So this gives us a roughly 30-year record to compare the performance of our system against observations. Okay, so the first question we can ask is, do Floor and SPEAR have seasonal sea ice extent prediction skill? And as a first look at that, here I'm showing predictions of Pan-Arctic September sea ice extent with the observations shown in black, and then predictions made at various lead times shown in color, with red showing the lead 0 predictions. So these are September 1st initialized forecasts, and then going back to a lead 3 prediction, which is a June 1 initialized forecast. We can quantify the skill using the ACC, or the anomaly correlation coefficient. And the ACC values in both systems are somewhere in the 0.8 to 0.9 range. So there's definitely some skill in these systems. Now, clearly some of this skill is coming from just the general ability of these systems to capture the downward trend in sea ice, which is obviously a key source of variability, over this record. So a more stringent test is to first linearly detrend both the predicted and observed time series, and then compute a detrended ACC. And what we see is that there's also skill at predicting these detrended interannual fluctuations, although the skill tends to be lower than what we get for the full time series. And we also see that the SPEAR system, especially at lead times of 0, 1, and 2 months, is doing better in terms of detrended ACC than the floor system. And I'll get back to why we think that is in a little bit. Okay, so one point that's become very apparent to us over the last 5 or 10 years has been stakeholders do not care about Pan-Arctic sea ice extent predictions. So Pan-Arctic sea ice extent is a single number. It tells you almost nothing about what your individual community will be experiencing in terms of sea ice conditions in a given month. And so we've been trying to push towards sort of more user appropriate forecast metrics. And sort of as an initial step towards that, we've been just looking at sea ice extent on the regional scale. So basically taking the Arctic and breaking it up into these 14 different regional domains, and then asking the question, can we predict sea ice extent skillfully in each of these 14 different regions? Okay, so I'm going to show a few different regional results here. And I'll start off with some regions of summer sea ice variability, namely the Laptev Sea and the East Siberian Seas, which are these seas along this Siberian coastline here. And I'm going to show a lot of plots like these ones. So what we're looking at here are detrended anomaly correlation coefficient values for different target months along the x-axis, and then different forecast lead times going from 0 to 11 months along the y-axis. And what you can see is that for predictions of summer sea ice, namely in July, August, September, and October, we have some skill going back to maybe 3 or 4 months in advance. And I should also mention that anywhere you see a square on these plots indicates that the skill of the system is exceeding that of an anomaly persistence forecast. And anywhere you see a dot on these plots indicates that we have significant skill, but we're actually losing to anomaly persistence. And then the other thing I want to note is that it looks like spear medium is doing better than floor in terms of skill. And the third column shows the differences between the two, spear minus floor. And you can see that sort of across lead times of 0 to 3 months, there seems to be some notable improvements in this newer spear system. So in order to try to understand those skill improvements, we need to ask the question, what are the key sources of predictability for summer sea ice extent in these systems? And so here I'm showing detrended anomaly correlation coefficient values in blue in the 2 different systems, and then again in the Laptev and East Siberian regions. And these are for September and plotted as a function of forecast lead time in months. And then the game we played here was we tried to construct a whole suite of very simple linear regression predictors to attempt to reconstruct the skill of the dynamical model. And after trying a whole bunch of different predictors, what we eventually came up with was a very simple set consisting of sea ice extent and sea ice volume, shown in black and red respectively. And we found that the combination of these 2 predictors was able to very effectively reconstruct the skill of the full dynamical model. And so these predictors are based on the initial conditions used by each forecast system. And these skill values I'm showing are simply the correlations between the initial conditions of extent and volume regionally with the observed sea ice extent that we're trying to predict. So the September Laptev sea ice extent, for example. And so what this tells us is that the key source of predictability for these summer sea ice regions of variability is sea ice extent persistence at short lead times. And then at longer lead times of 2 and 3 months, sea ice volume persistence takes over as the dominant source of predictability. And then these simple linear regression models can also explain the differences in skill between spear medium and floor. In particular, it seems that the main improvements that we're getting in spear medium appear to be attributable to improvements in sea ice extent initial conditions and additionally improvements in sea ice volume initial conditions. There may be some other reasons as well for these skill differences, but it seems like the initial conditions are kind of the primary reason for the improved skill in spear medium. Okay, so now I'm going to show just a few regions of winter sea ice variability, and I'm going to highlight here skill in the Barents Sea and the Labrador Sea. And we're looking at the same style plots showing detrended anomaly correlation coefficient values. The first thing that probably pops out to your eye is that the skill is much higher for regional sea ice extent in the winter as opposed to the summer. And we think the basic reason for this is that the winter sea ice anomalies have a stronger coupling to the subpolar oceans, and the ocean conditions, especially the upper ocean heat content in the subpolar seas, is fairly predictable on this time scale. And we think that's the key source of predictability for the sea ice in these regions. Again, we see that the spear system appears to show some improvements relative to floor in terms of its skill, mostly at shorter lead times in the Barents Sea, and then some longer lead skill improvements in the Labrador Sea. One thing I want to note here is that you actually see a pretty similar fraction of squares and dots on these plots, which again indicates that we are actually losing to persistence fairly often in these regions. So while these systems do have some skill at long lead times, which looks kind of impressive, it's important to note that we're actually losing to a very simple sea ice extent persistence forecast. So this isn't exactly an impressive achievement for these models. And so now we can ask the same question for winter sea ice extent, which is what are the key sources of predictability for winter sea ice in these systems? And we can play the same game where we can look at the skill of the models shown in blue, And then we're going to try to build a low-dimensional set of simple predictors to try to reproduce this skill. Again, we find that sea ice extent is a predictor does a very good job of reproducing the model's skill at short lead times. And as I mentioned, it also is doing very well at long lead times. So the sea ice extent predictor is actually beating the model's skill in most cases at these longer lead forecasts. Now, the sea ice extent predictor in the Labrador Sea especially does not do as well at these intermediate leads of 3 to 7 months. And that's because this corresponds to forecasts that are initialized over the summer, and the Labrador Sea is ice-free over these months. So there's no sea ice signal to persist. So we need to turn to some other source of predictability. And for that, we can look at upper ocean heat content. And what we find is that if we build a regression model using the upper ocean heat content initial conditions, it really nicely sort of fills in the skill between these two limbs of high skill based on sea ice extent. And so the idea is that we have some coherent sea ice extent and upper ocean heat content anomaly the previous winter. And then that anomaly is stored via the upper ocean heat content over the summer months. And then it reemerges again the following winter as the mixed layers deepen and the ocean's able to tap into these subsurface ocean heat content anomalies. And so sort of putting this all together, this says that the combination of sea ice extent and upper ocean heat content appears to be able to explain all, if not more than the skill of the dynamical models in this region. And the fact that these are beating the dynamical models in many cases indicates that we're definitely leaving some skill on the table in these systems. Okay, so now the final region I want to highlight here is the Chukchi Sea. So the Chukchi Sea is this blue region here, located just north of the Bering Strait. And in both systems, we find that there's fairly high skill for predicting sea ice in the months of June, July, and November. And then there's relatively lower skill for the months centered around the summer minimum in August, September, and October. And we had seen this skill structure in Floor and didn't really think about it too hard. We weren't sure whether to believe it or not, basically. But then the fact that we saw the same structure roughly emerging in Spear gave us some confidence to try to go after this and try to understand it a bit better. And so here I'm showing some similar plots to what I showed on the previous slide, where again, I'm using these three simple linear regression models based on sea ice extent, sea ice volume, and upper ocean heat content to attempt to reproduce the model's skill shown in blue. And if we look at the months of June and July, we see that this magenta curve, which is the upper ocean heat content predictor, does a very good job of capturing essentially all of the model's skill. So it seems like in these months, we're really in this ocean-based predictability regime. Now, if we move on to August, September, and October, there's this very striking drop-off in the magenta curve. So the magenta curve goes from being skillful in July to essentially having no predictive power in August, September, and October. And that's the case in both the Floor and the Spear medium systems. And we find that in these months, it's actually the sea ice extent and the sea ice volume that take over as the dominant sources of predictability. And then if we look forward to November, we see that the ocean heat content predictor jumps up again, and it's very skillful, and it's actually slightly more skillful than what we're actually getting in the dynamical models. So we have this sort of trade-off between this ocean-based predictability regime, a thickness-based predictability regime over the summer, and then a return of this ocean-based predictability regime in the month of November. Okay, so now the natural question is, why is there this trade-off between the thickness-based and ocean-based predictability regimes? And so as a way to get at that question, here I'm plotting the climatological ocean surface current speeds in the Spear model. And what you can see is that there's this fairly vigorous inflow of ocean waters through the Bering Strait. And that inflow kind of branches into these two different branches, one which travels north and then takes a right turn along the coast of Alaska, and it forms the Alaskan coastal current. And then a second branch which turns left and travels westward towards Wrangel Island here. And then the gray lines show the observed sea ice edge positions in all years of the observational record. And what you see is that in the months of June and July, these inflowing ocean waters are interacting directly with the sea ice edge in the Chukchi Sea. And so you can imagine that if there was some predictable signal in the ocean, it would be directly transferred to the ice edge in these months. And then when we get to the month of August, there's a fairly rapid retreat between July and August that occurs. And the ice edge is sufficiently far poleward that the ocean waters come in and they turn to the right before they're able to actually interact with the sea ice edge. And that's the case also in September and October for the most part. So this suggests that the ocean's able to exert less influence on the ice during these months, which is consistent with that drop in correlation we saw. And then eventually in November, the ice edge grows southward again, and it's able to interact again directly with these inflowing ocean waters through Bering Strait, and we recover this higher predictability based on these inflowing ocean conditions. So we think that the reason for this sort of handoff is due to the spatial structure of these inflowing ocean waters, and then the seasonal position of the sea ice edge position and how it interacts with those inflowing ocean waters. Great, okay, so just quick time check here. Okay, so regarding have we found that these two seasonal prediction systems do have skill for predicting regional sea ice extent 2 to 11 months in advance. And the skill is quite a strong function of the region you're interested in and also the season you're looking at. Okay, great. So now I'm going to move on to the final part of the talk, which is this will we question. And this part of the talk is going to be mostly focused on this phenomenon known as the spring predictability barrier for Arctic sea ice. And so I'm going to start with the definition. So I'm going to define the spring predictability barrier as a springtime date such that predictions initialized on or after that date can skillfully predict summer sea ice, whereas predictions initialized prior to that date cannot. Just as an illustration of that, here I'm showing the model skill detrended ACC values for the floor system. And what we see is that the skill tends to have this sort of triangular wedge type shape. And in these plots, diagonal lines correspond to common initialization months. So what we're seeing is that any forecast initialized May 1st or later is able to skillfully predict summer sea ice extent, whereas any forecast initialized earlier than May 1st, for example, April 1st, is not. So in other words, we have this spring barrier of predictability in these systems corresponding to roughly a May 1st initialization. Okay, so this this is where Dave Bonin enters the scene. So Dave may be familiar to a number of you at NCAR, and Dave came to GFDL as a Halling Scholar a few years ago, and he's now a PhD student working with Andy Thompson at Caltech. And when Dave showed up, the spring barrier had been identified in the floor model, as well as one other model. I think it was the HADGEM model. And so the question we wanted to answer in Dave's project was, is this spring predictability barrier robust across other models? Now, to answer this question, ideally what we would have is a suite of perfect model predictability experiments, which would let us estimate the upper limits of sea ice predictability for every GCM in, say, the CMIP5 or CMIP6 ensemble. We didn't have that, so we had to come up with some other way of diagnosing predictability across these different models. And we came up with the following technique. So we did have perfect model experiments run with the floor model. And so the perfect model ACC values are shown here. And again, we see sort of a diagonal skill structure in the East Siberian and Laptev Sea domain. And then in a similar sense to what I just showed, actually, we were able to build a very simple linear regression predictor model where we used earlier sea ice volume to predict sea ice area in different target months of the year. And what we found was that this very simple linear regression predictor based on sea ice volume was able to do a pretty good job of reproducing most of the skill of the full perfect model. So keep in mind that this plot here is the upper limit of predictability of this model. So we can't do any better than this. And we're able to reproduce most of that skill using just this very simple linear regression model. Of course, there are some skill differences, and especially at lead 0, there's skill kind of being left on the table here. That's because the main source of predictability, as I already mentioned, at lead 0 is mostly sea ice extent persistence. So the volume predictor does not do as well in this first month. But I would argue in months 1, 2, 3, and 4, the volume predictor is doing quite well, and it's able to capture most of the skill of the full perfect model. So this tells us that sea ice volume is the dominant source of summer sea ice area predictability across a range of regional domains. And then the nice thing about this is that we can then take this very simple technique of just doing these lag correlations between volume and area and apply this diagnostically to any model we want in the CMIP ensemble. So that's exactly what Dave did. He took control runs from CMIP5 models and computed these lag correlations. Here I'm showing the correlations for one such model. This is the access model. And again, we see that sort of that wedge type diagonal correlation structure. In these plots, the squares indicate the month of maximum decorrelation for each target month. So what we see is that consistently in this model, as we go from June to May, we're experiencing the maximum rate of decorrelation. And that's the case whether we're trying to predict June, July, August, September. In other words, these squares form a diagonal line, which suggests that there is a spring predictability barrier in this model. Here's another example of another GCM. This is the CAN ESM2 model. Again, a similar diagonal correlation structure and looks like a barrier type behavior. Here's the GFDL ESM2G. Again, qualitatively similar correlation structure. And then we can turn the crank and do this for every model in the CMIP5 ensemble. And what we find is that nearly every GCM in CMIP5 had this diagonal correlation structure to it. So this spring barrier appears to be quite robust across a wide range of different CMIP5 GCMs. Now, there are some differences between the various models. For example, the strength of these correlations can vary quite a bit between different systems. Also, the timing of the spring barrier was different between different models, with some models having more of a June barrier, other models having more of a May barrier. But I would argue that in terms of multi-model CMIP5 comparisons, this is a pretty robust result. And so this kind of raises the natural question then, what is the physical mechanism for this spring predictability barrier? And it's maybe a bit surprising at first glance that this barrier is robustly represented across all these different models. When we think that the sea ice model physics formulations are quite different across these various systems. The models all have different mean states. They have different representations of sea ice variability. So we want to try to understand this mechanism to understand sort of why this barrier appears to be so universal across these different models. And of course, with an eye towards trying to understand whether this barrier is actually a real feature in observations. So to get at that question, what we did is a sea ice mass budget analysis using daily data from two different large ensembles. So we looked at the Floor and CESM1 large ensembles. Both these use historical and RCP 8.5 radiative forcings. And crucially, both these large ensembles saved daily sea ice mass budget diagnostic data, which made all this analysis possible. So big thanks to CESM for saving this data and making it publicly available. So if we look at the mass tendency equation, in both models, the sea ice mass at a given grid cell can change due to top melt, side melt, bottom melt or bottom growth, and then a term involving the ice dynamics, which is this mass transport convergence term. And so I'm going to show three different diagnostics, a melt diagnostic, which encompasses top, bottom, and side melt, a growth diagnostic, which encompasses both congelation and frazzle sea ice growth, and then an export diagnostic, which is this mass transport convergence term. And just to give you a quick feel for what these terms look like, here I'm showing the sea ice mass budget climatologies in the Laptev Sea. And what we see is that in both models, we start growing sea ice in the fall. The sea ice growth rates peak around the month of November. They stay high through most of the winter, and then they start to fall off beginning in April. And then in sometime in the month of May, or in the case of CESM, later May, the melt term turns on, and the melt term hits a maximum sometime in the month of July in both models. And then in terms of export, what we see is that both models tend to have a negative contribution from the export term in the winter. What this means is that the export term is acting to transport ice out of this domain. So it's exporting ice out of the Laptev Sea in the winter. And then we see that the export values go positive in the summer, which means that ice is on the whole being imported into the Laptev Sea in the summer months. And then in the fall, it again turns back to a negative export value. And so these mass budgets, there's some differences between the models, but there's a lot of qualitative similarity, I would argue, between the two systems. So now what we can do is we can use these mass budget terms to do a mass anomaly reconstruction. And so we can take this evolution equation and we can time integrate these mass flux source terms on the right-hand side of the equation. And then we can break these source terms up into a climatological contribution and an anomalous contribution. And then what that gives us back ultimately is a sea ice mass time series consisting of a climatology plus anomalies coming from sea ice growth, sea ice melt, export, and then the initial mass anomaly. Okay, so now I'm going to show just one example time series. So this is showing the evolution of sea ice mass for just one particular year of one model. And I've converted the mass to an equivalent thickness, just so it's a bit more interpretable. So here we start on October 1st with a positive thickness anomaly of around 30 centimeters. And then as we go through the fall and winter months, you can see that the thickness anomaly kind of bounces around a bit. And then eventually we get to the summer and we see this growth in the thickness anomaly up to a value of around a meter. And then it persists through most of the summer until the end of the melt season. And we're going to see in a second that corresponding to this positive thickness anomaly, we have an associated positive sea ice concentration anomaly. Okay, and now what we can do is we can look at the individual budget terms to understand the contributions that each term is making to the sea ice evolution. So first I'm showing the growth term. And what we see is that the growth term is certainly not acting to drive this positive anomaly. It's actually doing the exact opposite. So the ice growth term is acting to pull the anomaly back towards its climatological value. And this is happening due to a negative feedback that occurs between ice thickness and sea ice growth rates. So in this case, the ice is anomalously thick. That means it's going to conduct less heat through it than normal. That means it's going to grow more slowly than normal. And so the sea ice growth tends to act as sort of a negative feedback on this pre-existing positive anomaly. And so the growth term is acting to kind of take away any predictability that is coming from sea ice thickness via this negative feedback. Okay, now in green here is the export term. And you can see that there's a very striking correspondence between these high frequency fluctuations that we see in the sea ice and the export term. And this is because these higher frequency fluctuations are happening due to the coupling of ice dynamics with synoptic variability in the atmosphere. So what we're seeing here is a series of storms kind of randomly sweeping over this region, and they're either anomalously diverging or converging ice into the region, and that's causing these thickness anomalies to kind of bounce around in a fairly unpredictable way. And then if we look at the melt term, it's of course off during the winter, and then the sun starts to come up in early May. And what we find is that the melt term is the term that's responsible for taking this thickness anomaly of around 0.4, 0.5 meters in May, and then growing it to a value of around 1 meter. And then that thickness anomaly persists through the rest of the melt season. And then, as I mentioned, we get a corresponding positive sea ice concentration anomaly, which is shown in cyan here. So these budget terms suggest a potential mechanism for the spring predictability barrier, in the sense that in the winter, the sea ice mass evolution is fairly unpredictable because it's driven by unpredictable synoptic variations in the atmosphere. And also it has this negative feedback happening from growth, which is tending to remove the anomalies. Nonetheless, the sea ice mass does this kind of random walk through the winter months, and it ends up with some anomaly in the month of May. And then we find that the melt term acts to take this anomaly and enhance it. And the reason this anomaly is getting enhanced is via the positive ice albedo feedback. So in this case, we have thicker ice. That ice is more extensive. So we get an ice albedo feedback associated with the areal extent of the ice. And then also this thicker ice tends to be both colder and also have more snow on top of it, which tends to increase the albedo and also tends to give us a positive enhancing feedback. So the idea here is that we have a predictability barrier because this ice albedo feedback response is highly predictable, but the dynamics that happen prior to the melt onset time are fairly unpredictable. Okay, so we can look at this a bit more carefully by doing a formal covariance decomposition. So what I'm showing here are the covariances between sea ice area at a given date. I'm showing September 1st in these plots, and then earlier sea ice mass anomalies. And so the full covariance is shown in this magenta curve. And then what we can do is we can use the fact that the covariance operator is linear, and we can decompose this full covariance into contributions from each of the budget terms. And what we see is that there's this signature of the spring predictability barrier where we get this rapid growth in covariance starting in the month of May. And what we see is that it's quite clearly in both models, this melt term turning on and then driving this rapid growth in covariance that's giving us this rapid increase. And that's the case in both floor as well as CESM1. The export term shown in green also contributes a lot of positive covariability. So there is a lot of sea ice predictability coming from the export term. But in terms of setting the barrier timing, there's no real change in this curve corresponding to June 1st in this model or in CESM. So the export term kind of grows monotonically, but it's really the melt term turning on that causes this rapid growth in covariance starting in the spring. And if you sort of squint at these curves, you can see that there's a difference in melt onset between these two models, where the melt onset is around the middle of May in floor, whereas it's closer to June 1st in CESM. And if we look at the same sort of lag correlation plots again, you can see that corresponding to this shift in melt onset timing, the barrier is shifted correspondingly by about 2 weeks between the two models. So it seems like the barrier in floor is around a May 15th barrier, whereas in CESM, it's closer to a June 1st barrier. And this seems to be set by the timing of melt onset in the two models. Okay, so I think I'm going to wrap up right away. I still have a lot of time for some questions, but just the one final point I want to make is that these results suggest that sea ice thickness observations are especially critical between June 1st and September 1st. And unfortunately, the current observations from satellites of sea ice thickness terminate around April 15th. And that's due to the presence of melt ponds on the ice surface and the fact that these melt ponds corrupt the sea ice thickness retrieval algorithms. Now, there's been some really nice work done over the last couple of years by Jack Landy, and we've been collaborating with him on this. And Jack's produced the first ever year-round data set, which includes summer sea ice thickness observations from the Cryosat-2 satellite. And so he's produced this 10-year record spanning 2010 to 2019. And then he's computed the same sort of lag correlations that I've been showing over and over again. And we again see in the observational record that there appears to be evidence for this spring predictability barrier in the observed thickness. And then really excitingly, if you look at the predictions of September, for example, there's very high correlations between observed September sea ice extent and then Jack's sea ice volume data set. And that's shown in this purple curve on the right here. And so we're getting correlations of above 0.8 going back to the middle of the month of June. So this suggests that if we could get these new thickness observations in the summer into our prediction systems as initial conditions, there's some really exciting potential to improve the prediction skill. One big warning is that this is only a 10-year record. So computing correlations over a 10-year record is, of course, quite a dodgy thing to do. But I would argue the fact that these correlations are so high indicates that I think there is something real in this record. Great, so I'll just quickly wrap up with a few conclusions. So we've shown that the spear and floor prediction systems skillfully predict both Pan-Arctic and regional sea ice extent 2 to 11 months in advance, depending on the region and the season of interest. And we found that this combination of regional predictors based on sea ice extent, sea ice volume, and upper ocean heat content can match or in some cases exceed the skill of the dynamical models. And we therefore advocate using these 3 simple predictors as benchmark tests for evaluating Arctic seasonal prediction systems. We found that the spring Arctic sea ice predictability barrier is a robust feature of CMIP5 models and also seasonal prediction systems. And we argued that the spring barrier results from this combination of unpredictable wintertime mass variations driven by export and ice growth and predictable mass variations driven by ice albedo feedbacks beginning in the month of May. And then finally, this new summer sea ice thickness observational data set has some exciting potential to improve summer sea ice forecasts. And so these are the references of what I spoke about today. And I just want to say, yeah, big thanks for listening, and I'm happy to take any questions you might have.
Thank you, Mitch, for very interesting talk. Any questions from the audience, feel free to raise your hand or put them in the chat. Yeah, Marika, go ahead.
Hi, Mitch. Really nice talk. So I had a question about one of the results you mentioned early in your talk, that it looks like models are too predictable. Do you have any ideas as to why our models are too predictable?
I mean, the first thought I guess I have is missing physics, potentially. Missing physics, which is inherently unpredictable. One possible thing could be that the models generally don't include interactions with waves, and also don't really resolve sea ice flow size distributions until recently. And so I could imagine having waves in the model is just an extra mechanism for breaking up the ice, making it more susceptible to atmospheric forcing. And I would think that, that noisy atmospheric forcing would reduce persistence generally. So wave coupling is one possible candidate. I'm sure there's some other candidates, but that's the one that kind of comes to the mind off the top of my head. But yeah, missing physics, I guess, would be my short answer. But if you have ideas, I would love to hear them. I really don't have a great answer. Yeah.
That's one of the processes that comes to my mind too. I guess the follow-on question to that is, are you moving towards including wave ice coupling and a flow size distribution in future versions of your prediction systems?
Yeah, great question. So as you know, like the SIS2 sea ice model it's around a SICE version 4 right now in terms of its sea ice physics. So we're still kind of like, we don't have mushy layer thermodynamics in here yet. We don't have melt ponds, and we also don't have ridging as well. So we're hoping to add those 3 pieces in first. And then I think after that, the FSD and maybe wave coupling would be sort of the next on the list. So certainly we want to do that and hopefully kind of evaluate the impact of sea ice physics on prediction skill as well as we're sort of going through this. In addition to sort of the standard kind of climate model tuning type exercises that we're going to do as well. So yeah, it's kind of on the docket, but probably a few years away, I would guess.
Yeah, lots of interesting stuff to do though. Thanks.
Yeah, thanks.
Lorenzo, go ahead.
Yes, hi Mitch, very nice talk. I have a question about your anomaly mass budget. So it seems that the dynamical terms responds quite well to the atmospheric dynamics, so to the storm passing. And I would expect also the melting term to behave similarly, because there are good evidences that when a storm reaches the ice, then the melting is enhanced, because also we get more mixing. So are we missing something in terms of model physics, or yeah, maybe you can comment on
yeah,
this.
That's a great question as to whether or not this coupling is actually sort of sensitive enough to the high frequency variations. I would argue if you squint at this melt curve, you can see that there seems to be sort of a storm event here where there is a dip in melt and there's another kind of bump up in melt here that does seem to be in phase with the dynamical piece. So that might be storm related. I don't really have a good answer for whether it's actually quantitatively correct or not, or if there's enough variability in the melt. I would certainly expect the melt to be a bit slower, just because it's dictated by the SSTs basically, and the surface skin temperatures, which are a bit more of an integrator than the ice dynamics themselves. So I would expect these fluctuations to be a little bit less than the green line, but yeah, I don't really have a good answer, to be honest. It'd be great to look into that.
Thank you.
Yeah, Dave, go ahead.
Kind of a snarky question. So I was wondering, where was the floor and the spear system on the SIP-in prediction chart you showed?
Yeah, so good question. So floor was yeah, it wasn't on there. Maybe, and that's maybe what you're referring to. Awesome.
Yeah.
So we submitted predictions with floor from 2014 to 2020. And then, as I mentioned, floor was retired in 2020. We stopped running it. We started running spear at that time. And what we found actually was that when we transitioned to running spear in real-time mode, we were getting very strange prediction results. And it took us 6 or 7 months to finally track down what the issue was. And it ended up being an issue with the input SST observations that we were using in the system. And basically the SSTs, when we ran in real time, it was an interpolation issue. It was a temporal interpolation issue. In the hindcast, to get the SST on the 31st of the month, we were actually temporally interpolating between the 30th and the 1st of the next month. Whereas when you run a real forecast, you can't do that. And there was actually just basically a bad value that was getting interpolated into the SST field, which we did not realize until quite a bit of digging. And that was basically messing up the sea ice forecast. So it's straightened out now, and we are going to submit this summer, but 2021 was an unfortunate outage for us. So yeah, good catch there. Yeah.
Yeah, Lorenzo.
Maybe just a very quick question. So about the difference between the floor and the spear system, you showed that there is a jump in initialization skill, also related to the volume, but in the end, you're not assimilating any thickness information. Is this enhanced thickness skill due to a reduction of model biases, or is it due to the assimilation of the concentration?
Yeah, great question. So the extent improvement, as you mentioned, is due to the fact that we use sea ice concentration in this very crude way. Like we're using concentration in sort of a sea ice extent assimilation kind of mindset, where if the grid point is ice covered, we set the SST to the freezing point of the model. And we find that works pretty well at getting the extent right. That gives you no information though about the thickness. And so we think that the thickness information in the system is coming from the fact that we are doing this nudged run of the full coupled model, where we nudge both the atmosphere and the SSTs. And we think we're getting thickness information from the fact that we're basically nudging to the observed temperatures and winds, which are giving us dynamic and thermodynamic constraints on top of the sea ice in the thick ice regions in the high Arctic. Now, why those are better in the floor system also had an air temperature constraint. One slight difference is that floor only had an air temperature constraint, whereas spear also has a wind constraint. And so in floor, the winds were updated via covariances with temperatures, which gives you some of the information, but not all of it. So it may be that the winds are better in the spear system, which gives us a better representation of this sort of synoptic type variability. But yeah, don't fully understand yet. But I think that's the basic reason, is basically our use of atmospheric reanalysis. Which kind of brings me to another point, is that I would love to try your new improved reanalysis whenever it's ready. And maybe that would make this even better potentially.
Yeah, happy to discuss more about this.
Yeah, for sure.
It makes sense what you said.
Okay, well, we're 1 minute past the hour, and I want to be respectful of everybody's time, especially since it's lunchtime here in Colorado. But I want to thank Mitch again for a very interesting talk, and we'll see everyone next week.
Great. Thanks, everybody. Thanks a lot, Patricia, for moderating. Appreciate it.
Yeah, of course.
Bye, Mitch.
Yeah, see you, Lorenzo. See you, Marika.